Hi everybody, in this video we are going to go over section 5 of chapter 8 and we are going to talk about complex numbers from a trig perspective or a polar perspective. First we're going to introduce this idea of a complex plane and then talk about the vector representation of a complex number, which should make sense to you because remember, a vector is a quantity that takes two items to represent it. Well, a complex number is also a quantity that actually has two, which is actually represented by two items, the imaginary part and the real part, since it makes sense that this should be a vector. Then we will introduce the trigonomic form of a complex number, talk about how to convert between standard form and trig form, and then show how we can use the trig form to compute the product and quotient of complex numbers, which actually makes this operation a lot easier when it is in trig form. Okay, so what is the complex plane? Well, if we start with the Cartesian plane, change the y-axis, x-axis to the real axis and the y-axis to the imaginary axis, we have a complex plane where the horizontal axis is the real axis and graphs the real part, and the imaginary axis graphs the imaginary part. And as you can see, here is a complex number, and as you can see, it is represented as a vector. Which brings us to this. Notice that vectors, once again, are described using two items, typically the horizontal component or the vertical component, or the magnitude and a phase. Well, since a complex number is described using two items, namely the real part and the imaginary part, it makes sense that we should be able to represent a complex number on the complex plane as a vector, and indeed we do. The complex number is nothing more than a position vector where the initial point is at the origin and the terminating point is at the point AB if your complex number is A plus BI. If you've taken 115 or something equivalent, you have learned that this right here is called the standard form of a complex number. Well, as you can see, it kind of forms a rectangle when you plot it, so it's also the rectangular form of a complex number. And of course, then the sum of the two complex numbers is essentially the resultant of the corresponding vectors. So you can use all the tools that we learned in the previous two sections to actually compute the sum of two complex numbers. Of course, the easiest way to do that is when they are in standard form or rectangular form, because the sum of those two complex numbers is just the sum of their components. And this brings us to this particular example. Notice I forgot to put example 1 down. Shame on me. Okay, so here we want to find the sum of the complex number 2 plus 3i and the complex number negative 4 plus 2i. And how do we find the sum? Well, essentially we add the real parts and then we add the imaginary parts. So 2 plus 3i plus, almost forgot that, negative 4 plus 2i is going to be the sum of the real parts, which will be 2 minus 4 plus I times the sum of the imaginary parts, which will be 3 plus 2. And that will give us negative 2 plus 5i. And then the next part is to graph the two numbers and the resultant. Well, we don't need to do that. We just need to recognize the correct graph. And that is pretty easy. And here are four options, which are basically consistent with what you're going to see in MML is essentially the correct set of numbers, just rotated around a little bit. So the first complex number we're looking for is 2 plus 3i. Well, this is 2 plus 3i. Okay, that one is right. This one is, I'm sorry, no, actually that's negative 2 plus 3i, so that one is wrong, so that one's out. This is negative 2 minus 3i, so that one is out. This is 2 minus 3i, so this one is out. Here is 2 plus 3i, so this one works. For the next one, we have negative 4 plus 2i. Negative 4, 2i, there you go. And our resultant is negative 2, 5i, so this right here obviously is the graph. Now we want to introduce the trigonometric form or the polar representation of a complex number. And what we're going to do is take advantage of these relationships. Notice here we have a vector, we can just call it the vector u for the time being, and it comes up to here, and notice that we can form right angles with the horizontal and the vertical projection. As a consequence, using what we know about the definition of cosine and sine, we can say that the horizontal component is nothing more than r cosine theta, the vertical component is r sine theta, the magnitude is going to be the square root of the sum of the squares of the components, and the angle is going to be that angle whose tangent is equal to the ratio of the opposite over the adjacent, of course, and is also in the correct quadrant. So with that in mind, if this is a vector representing the complex number x plus iy, the trig form is going to be r times cosine theta plus I sine theta, where the x component, the horizontal component, is r cosine theta, and the vertical component is r sine theta. And obviously what we're doing is we're factoring out the r. Now, we actually do have an abbreviated form, and that form is basically taking advantage of the fact that we can write a new function called CIS. I just call it CIS. I don't know if you could say KISS, I suppose. And that is equal to cosine theta plus I sine theta. If that's the case, then you can actually write this in a more compact or abbreviated form right here. And you will see this a lot. And actually, we are going to write this at the very end to an even more compact form, which will make a lot more sense. So this right here is the rectangular form for a complex number, and this are the trig forms for the complex number, where r is equal to x squared plus y squared, and once again theta is that value of that value whose tangent is equal to y over x, and for that, which is also in the correct quadrant. Okay, and of course, now our next example is going to be to take something that is in trig form and write it into rectangular form. And that is a relatively straightforward endeavor because there are no ambiguities that you actually have to deal with. Okay, so to do that, we need to figure out what the horizontal component is. We're going to call the horizontal component x to kind of associate with the x-axis. That is going to be equal to 10 times the cosine of 135. Now the cosine of 135 is actually equal to the cosine of 45, but since we are in the second quadrant, it'll be negative. So this will be equal to 10 times the negative root 2 over 2. And if we simplify that, we will have negative 5 times the square root of 2. Now y is going to be equal to, well, this will be the imaginary part, 10 times the sine of 135. That will be equal to 10 times, oh, I forgot the 5 there. Well, the sine of 135, and the sine of 135 is just like the sine of 45, but 135 is in the second quadrant. But it turns out that in the second quadrant, the sine is still positive, so this will be the square root of 2 over 2. And then that will be equal to 5 times the square root of 2. And then in rectangular form, we will have negative 5 times the square root of 2 plus I times 5 times the square root of 2. And that right there is rectangular form. Now, converting from a rectangular form to a trig form is not as straightforward. And why? Because there is an ambiguity relative to the angle. For example, there are two quadrants where the angles have the same value for tangent. In quadrant 1 and quadrant 3, tangent is positive, and in quadrant 2 and quadrant 4, tangent is negative. So we actually have to make sure that we are computing the right angle. And to do that, we basically need to draw a picture. We can draw a picture, make sure we understand which quadrant our complex numbers want to lie in. Once we've determined that quadrant in step 2, then we can find r using the Pythagorean theorem. And then we can find theta using this value, which basically results to trying to figure out what the arctangent of y over x is. And once we found that particular angle, then we need to adjust that angle depending upon what quadrant we are in. For example, because arctangent will produce for you a value in these two quadrants. So if your vector lies in this particular quadrant, you can take whatever angle you get, and that's your angle. However, if your vector lies, or if your complex number lies in either quadrant 3 or quadrant 4, then you will have to take whatever this value is and add 180 degrees to it, or pi, depending if you're working in radians, to get the correct angle. And that's basically the thing that you have to be careful about. And we will demonstrate that in these two examples. And here's our first one. This should be negative 8 minus 8i. My apologies. Now, for the first one is to draw a sketch, and here is our sketch. And then step number 2 is to determine which quadrant we're in. Well, if this is negative 8, which it should be, minus 8i, we are in quadrant 3. And since we're doing radian measures, the quadrant, the angles associated with that quadrant are going to be all the angles between pi and 3 pi over 2. Theta must be in those particular ranges. All right, so now we have that established. Okay, so now we can go ahead and figure out what r is. Well, r is going to be the square root of negative 8 squared, which is 64, plus the square root of negative 8 squared, which is 64, which is equal to, you could write this as 128, but you probably don't want to, because you can also write this as 2 times the square root of 64. Well, the square root of 64 is 8. Square root of 2 is the square root of 2. There you go. You're done. Okay, now what about theta? Well, we know that we have that y over x in this case is going to be equal to 1. Okay? Then the arctangent of 1 is going to give you pi over 4. Well, this right here is pi over 4, and once again, we are in quadrant 3, not quadrant 1, so we need to add pi to this. So our angle theta is going to be this result, pi over 4, plus pi, which will give you 5 pi over 4. And now we know everything that we need to actually write this in trig form. And I'm going to use the non-abbreviated form. This is going to be equal to 8 times the square root of 2 times the quantity cosine of 5 pi over 4 plus I times the sine of 5 pi over 4. Okay? And that is our answer and that is our complex number in trig form. Now for this particular case, it actually is a special case, but it actually is a little bit easier. But nonetheless, let's actually go through our steps. First one is to draw a sketch. Here it is. Determine which quadrant it lies in. Well, it doesn't lie in any quadrant. It's actually a quadrantal angle, so it lies in no quadrants. However, by inspection, we can just determine that theta is equal to 270, since we're doing degree measures. I mean, it's pretty easy to figure that out. Okay, so that's basically step 2. Actually, this also is step 4. Step 3 is to figure out what r is. Well, remember, we can write this as 0 minus 5i if you actually wanted to be very explicit. And then r is going to be the square root of the square of the real part, which is 0 squared, plus the square of the imaginary part, which is 25. That will give us the square root of 25, or 5. Now, for theta, once again, we have that y over x is undefined. So we really cannot use that approach. That's not going to work for us. But by inspection, we can see that theta is equal to 270. So with that point, with that in mind, we are pretty much done. We know what theta is. We know what r is. We can actually write this as 5 times the cosine of 270 degrees plus I times the sine of 270 degrees, and there it is in trigonometric form. Okay, now you also might be asked to do this during using a calculator, and let's go ahead and do that for this particular case. Now, first step, of course, is to graph our function. Here it is. Notice that we are and recognize the quadrant. Well, we're in quadrant 2. We're going to be using degree measures, so our degrees, our angle is going to be between 90 and 180. Okay, so that's step 2. For 3, we're going to figure out what r is. R is going to be the square root of the square root of the real part, which will be 7 squared, or 49, plus the square of the imaginary part, which is going to be 2 squared, or 4. That gives us the square root of 53, and we're going to leave it just like that. We're not going to evaluate that with a calculator. What we are going to evaluate with the calculator is the angle. So we know that y over x is going to be negative 2/7, and that the tangent of theta is going to be equal to negative 2/7, which means that the arctangent, and it's going to be in quadrant 2, and the arctangent of negative 2/7 is equal to negative 15.94540 degrees, which is this angle right here. And of course, that's not the angle we want. We want the angle in quadrant 2. How can we find that? Well, we can take the output of our arctangent function, which is negative 15.94540, add 180 to it, and we get what we want, which is 164.0546. We're probably just fine rounding this to the 100th digit, and that's the case. And our complex number in trig form is going to be the square root of 53 times the cosine of 164.05 degrees. I should have degrees up here as well, plus I times this, oh no, parenthesis there, my apologies, sine 164.05 degrees. And there you go. Let me go back to my previous example back here. Okay, those are right. Just wanted to make sure. Okay, and that brings us to the next topic, which is the product of complex numbers in trig form. Now, we've dealt with products of complex numbers in rectangular form. There, if you actually had the complex number a plus bi, multiplying that by c plus di, you actually have to use FOIL. And you get 4 terms, and 2 terms are real, and the other terms are imaginary. So it's kind of a tricky little process. When you actually have your complex numbers in trig form, it is a lot simpler. And here's the theorem. Let's suppose you have two numbers. One is r1 cosine theta 1 plus I sine theta 1. The other one's the exact same thing with the subscripts 2. Then the product of those two numbers is going to be the product of the magnitudes, and the sum of the angles. That's all that it is. The product of the two numbers is going to be, once again, the product of the magnitudes, the sum of the two angles. Okay, you want to see that in an example? Well, of course you do, and here we are. We want to find the product of 4 cosine 120 plus I sine 120 and 5 cosine 30 plus I sine 30. Well, once again, that is going to be equal to the product of the magnitudes, 20, times the trig form with the sum of the angles. So it's going to be 20 times cosine of 20 plus 30, or 150, plus I times the sine of 120 plus 30, or 150. Okay, and those we can actually compute exactly. This is essentially an angle which is 30 degrees off of 180. So right here is 30. This is 150. So the cosine of 150 is actually the cosine of 30, but it is negative since you're in quadrant 2. So this is going to be negative the square root of 3 over 2 plus I, and then the sine of 150 actually is equal to the sine of 30. This will be 1/2. And now we need to write this in rectangular form, which means we need to multiply this through, and that will give us negative 10 times the square root of 3 plus 10i, which would be our answer. Notice how much easier it is to do this in trig form than it is to do this in rectangular form. Same applies for dividing two complex numbers or finding their quotient. If you have two complex numbers the exact same form, then their quotient is going to be the quotient of the magnitudes times our trig form here, where the angle is the difference of the angles. And of course I have that proof for you worked out in your notes, and if I feel so inclined I might do it here. But notice how this is a lot easier than the case where you would have a plus bi divided by c plus di, because in this particular case you actually have to multiply both sides by the conjugate of the denominator, or the top and bottom by the conjugate of the denominator, which would be c minus di, and then you had to work all that stuff out. In this particular case, you do not. All you got to do is take the magnitudes, the quotient of the magnitudes, and then the difference of the angles, and you are good to go. Okay, and here's an example where we actually have to do that. Okay, once again, we are going to take the quotient of the magnitudes. That's going to be 27 divided by 9, or 3. Then we are going to have CIS, the difference of the angles, which is 45, minus 180. That will give you 3 cosine times sine, or cosine I sine, I guess you could call that, of negative 135 degrees. I forgot my degrees here and here. Now, we really don't want to work with a negative angle. We actually want to work with an angle between 0 and 360. So it might be good to find the coterminal angle, an angle between 0 and 360 that is coterminal with that. And we can do that by taking negative 135, and adding 360 to it. And if we do, we will get 225. That's an angle that we can work with, and basically 225 is in quadrant 3 right here, and we have a 45-degree angle between 225 and 180. So the reference angle is 45 degrees. So this is equal to 3 CIS 225 degrees. Now we need to write this in rectangular form, and it's probably easier to get into rectangular form if we if we write this in the expanded form, which is 3 times cosine of 225 plus I times the sine of 225 and remember the reference angle is 45 degrees. We are in quadrant 3, so both cosine and sine are negative. So that will give us 3 times, well, cosine of 45 is root 2 over 2. However, it's negative, minus I root 2 over 2. And then our final answer is going to be negative 3/2 times the square root of 2 minus I times 3/2 times the square root of 2. And that would be our answer in trigonometric form. There is one more thing I want to point out, or want to show you, is actually not part of this section, is not part of this course, but it is interesting nonetheless anyways, and it kind of helps put the idea of multiplication and division of complex numbers, at least in trig form, in some perspective. And that is Euler's formula. Euler's formula says that that Euler's number, E, the base for the natural logarithm. E raised to the I times theta power is equal to cosine of theta plus I sine theta. And what does that mean? Well, that basically means that any complex number in trig form can be written in this, and we can call this exponential form. And from here, the idea of multiplication and division comes out naturally. For example, what is the multiplication of two complex numbers? R1 e to the I theta 1 times R2 e to the I theta 2. Well, I mean, we know how to do how to multiply exponentials or numbers with exponentials in it. This is going to be R1 times R2, and then we're going to have e raised to the I, or raised to the sum of the exponents, which will be I times theta 1 plus theta 2. Similarly, it works out for quotients just as well. For example, R1 e to the I theta 1 divided by R2 e to the I theta 2. What's that? Well, it's going to be the issue. It's going to be equal to the quotient of R1 and R2, whatever that is, and R2. And then as far as the exponentials, well, that's going to be the base raised to the difference of the exponents, I theta 1 minus theta 2, which is consistent with what we discussed here and here. And that is all that I have for this particular section. If you have any questions, please feel free to reach out to me. This is Bob Boylan, signing off.